Welcome back. So yeah, last time we briefly talked about effect sizes, and we briefly defined meta-analyses, and we have also defined effect sizes. Today I want to briefly talk about effect size measures in single group designs. So the first, actually most commonly used effect size measure is mean. So mean is one of the most commonly used central tendency measure, and it's rather infrequent actually as outcome measure, but you can use it mainly for let's say if you are interested in the mean height or in the mean weight or something, or maybe in the mean glycated hemoglobin levels or something, then you could probably be interested in the mean. So meta-analysis is also possible. You can synthesize mean using meta-analysis of means, and I will briefly simply talk about what is mean, and then later on we will dive into combining means. So the mean, the formula how to calculate mean is very simple. You simply sum all the observations, the values of the observations, and then you divide it by n. And then afterwards, you would be very much interested in finding out the standard error, because you need this value for synthesizing the means. You want to synthesizing or for meta-analysis. So that means you need the mean and the standard error. So if you want to combine the meta-analysis if you want to do meta-analysis of means, that means the first thing you need to have is the number of observations. That means the sample size of the study, and then the other thing you need is the mean that's reported in the studies. And then afterwards, you need the standard deviations, which you will be able to convert it to standard error, and then you can use it to get to your meta-analysis. Having said that, we will continue. It's a second effect size measure in single group designs, and that is proportion. So proportion is actually another type of mean measure. It's not mean, but it's mainly central tendency measure for categorical or maybe categorical outcomes. For example, if you are interested in studying the prevalence of a disease or the proportion of people who live with diabetes or HIV or something, or any other chronic disease, or any other any other measure, then you would be interested in finding out proportion, for example, prevalence of a disease. So for that, what you need, how to calculate fluid proportions. What you need is a K. That means the number of people falling in that group in one particular, or the number of people having a certain disease divided by the total number of people. And then the other thing that you would be interested to have is the standard error. And to calculate the standard error, you will have to use this formula. That means proportion times 1 minus p, or the complement of proportion, that is the total number, that is this one, the value here, and then the complement is a q, that means 1 minus p divided by n. So to do meta-analysis of proportions, these are the two main things that you need. You don't need anything else. You just need to have the number of observations which are specific to subgroup K, and then the other one that you need is the total number of observations. That's to sample size. That's what we need to calculate to conduct meta-analysis. Because actually, for proportion, the proportion usually lies between 0 and 1. So that means this distribution is skewed. So that means it's skewed. So you have to, because it's always lying between 0 and 1, that means it's the distribution will be right skewed, or left skewed actually, because it's also impossible if you want to do random sample and to have calculate the proportion outside of 0 and 1. So you don't have negative proportion, or maybe you cannot have proportion outside bigger than 1. So that means your distribution will be skewed. So to avoid that, what you need to, before you combine it in your meta-analysis, what you need to do is you need to transform it, and that transformation is called log transformation or log transformation. So then once you do the log transformation, you will be able to get the p log it, that means the prevalence here, or the proportion, that will be converted into p log it, and then once you have the p log it, you will be able to, you need to have another which is the standard error. So let me actually link the formula maybe to get actually the log it will be, you simply pass the prevalence formula here, you simply pass it like this. So what you need is you convert it, you need to transform it into log it, so that means you will have log it p over 1 minus p. That's actually the way you calculate the odds ratios, logos. So you calculate the logos, and then once you get the logos, you can also get the standard error of this period. So as I said, it is not actually that I want to put here, it was supposed to be here. Sorry. So once you get the p log it and the standard error of the log it, then you'll be able to combine. You'll be able to combine them in your meta-analysis. Luckily, in the meta-analysis, the R performance, you don't have to do this manually. That means you don't have to transform it. I mean, you can do it, but the package that are available in R, the metan or the metaphor package, they will handle this for you. And that's what you need to feed to the function of the metan or the metaphor package is the number of events or K, and then by the total number of the size, then what the sample size. Once you have that value, then the software will be able to do the synthesis of the proportions. So that means you will have a meta-analysis of proportions or meta-analysis of prevalence or something. It's a relatively very easy thing. But although there are people who are really against combining prevalences, because there could be more population heterogeneity and things like that. So you have to consider when you combine these prevalences, you need to have a very defined population. Otherwise, you will have to you may have to mix. You may be mixing apples with oranges, even if they are they are a similar concept. Unless they are in a similar defined population, then you may be biasing your synthesized proportion. So the other outcomes that the other measure, effect size measure in single group designs that you may encounter is correlation. Actually, correlation, the way you calculate correlation is this is how you calculate correlation. That means the sigma square of xy between the x and the y variables, and then you divide it by sigma x and sigma y. That's similarly, similar to what we see in proportion. There is again the skewness here, because correlation is always lying between -1 and 1, so it doesn't go outside this range. It's always between -1 and 1. So it's always between -1 and 1. It doesn't go outside of 1. So it always lies between this. So that means your distribution is skewed. So because it is skewed, you need to find out a mechanism how to transform this skewness. So that is already in the package. So likely, the package is already there. So the way you do it is like you need to have the Fisher Z transformation. Actually, it's called Z transformation. And let me just drop you one formula how to do that. The way you do that is you need to get the Z transformation. Let me just bring it down. So this is how you do the Z transformation in for correlation. So that means you multiply 0.5. This is just a constant, and then you pass it with a natural logarithm, and then you simply 1 plus r over 1 minus r. Then once you have that, you will pass it with 0.5 times log e, and then you get the Z core. It's called Z core or Fisher Z transformation. And once you have that, you will also need a standard error. For the standard error, you will get this formula. That means it's actually supplied by, it was introduced by Fisher Z and can be obtained through the formula by Olkin, Olkin and Finn. They introduced this formula. So that's the standard error of the Z transformed correlation. The one we transform. Once you transform it, then you will calculate the standard error. Once you have these values, it will be easy to calculate the meta-analysis. Again, you don't have to do this manually unless you want to. The software can do the Z transformation. I mean, you need to supply it that you will need to transform it to Z core, and then the values that you need to synthesize correlation is you need to have the correlation value, of course, and then the total sample size. That's what you need to have for the correlation. Maybe we can quickly have a look how you do this Z core transformation manually if you want. Let's just create a quick demo. So let me just do this, and then so that it can be reproducible. Then once I have that, let me just give x value. The x value, let me give it r norm, and then that r norm would be 20, 50, and then let me give it this. Then the y, let me give it again r norm 20, r norm of 10, and then the standard deviation of 3. That means if you do r norm, you can check what r norm is. That means the sample size is 20, and the mean, I'm giving it the mean of 50, and the standard deviation of 10. Then r norm, the total sample size is 20. I just need 20 respondents, 20 observations, and the mean of that total observation is 10, and then the standard deviation is that's what r norm is. Actually, you can check it yourself also. R norm, yeah. So that means you have x, that means, and then mean, x is the total number of observations that you need. So let me just do this, and then we already have these values. Then once you have these x and y values, we can simply correlate them. For correlation, what you need is r4 times actual core, and then simply xy. Let me store it as r, and then we print out r. How much is it? So r is showing is minus 0.97, and as I said before, we want to transform it into this Fisher Z core transformation. For doing Z core transformation, the first thing you remember, this is a standard error. But if you remember for the z-code transformation, the formula that we get is this one. So you get z 0.5 log e 1 plus r 1 minus r. You can create your own function, like you can do z-code transformation if you want, and then you get this function, and you simply give it what do you need. What you need is r value, and then you give it with maybe this one. If you want, you can create the function yourself. Function r, that's the correlation value that you need, and then what do you need? The z transformed value equals 0.5 times what was the formula? Okay, 0.5 times log, then you give it 1 plus r divided by 1 minus r. That's what you need to transform the z-code transformation. Remember our z-code transformation value, I mean before transformation it was minus 0.9. Then we will transform it, and then we will have the z transformed correlation. So now we should be fine. Log 1 plus r. Because log is for the whole group, so we simply pass it. Then z-code transformation will be the function r, and then z transform 0.5 times log 1 plus r divided by 1 minus r, and then the return will be z-code transformation. Then we just pass this, what I need is the z-code transformation, and then I just need the r values that I already defined here. Now I should get the z-code transformation value, and that means yeah, it's not very different, but it's a little bit different. So that means this is it's somehow transforming and normalizing your correlation values. The next thing you need to do is you need to of course calculate the standard error if you want. If you remember that formula, the formula that I showed you before is the standard error is 1 minus one over n minus 3. So we already have like 20, the sample size was 20. So 20 is the standard error of the z. So just 1 over square root of 20 minus 3, that's 17. That's the standard error of our correlation here. So that's what you need. Once you have that, you will be able to, once you have all of for many studies, like more than 2 studies, then you will have you already calculated the z-core value, and then you have the standard error of the z-core is z transformed correlation. That's the Fisher transformed correlation value. And then once you have that, you can calculate the standard error. Once you have these values, you don't need anything else. You can then be able to combine it in meta-analysis. So but thankfully, you don't need to do all of this. You don't need to do all of this in your analysis. You simply supply the correlation value in your meta-core function. That's what you do. The meta-core function requires meta-core function. The meta-core function in metan simply uses the correlation value and then the sample size. Once you have that, and then you do the other ones. I mean, you give it a study ID and things like that. When you see that, then yeah, the software will do it for you. That's how you do transformation, and how you can supply it to your function the correlation. But there is another correlation, that is pointwise error correlation. The one we saw is the usual kind of correlation that you know. It's called Pearson product moment correlation. But you can also combine Kendall correlation. There are something. I mean, sometimes you need to have Pearson correlation, and you have Kendall Tau correlation, and you have other. What is the other one? There are three different kinds of correlations. Sometimes you may have difficulties because some studies may report Kendall correlation, others may report Pearson correlation. So you may have this kind of conflict. So you will have to you will have to decide whether you will combine this Pearson. Actually, let me see because the method you defined, the methods are like a Spearman, that's what I wanted to say. So you have Kendall, Spearman, and Pearson. So some studies may report the Pearson correlations, others may report Spearman correlation. For the same, for example, if you want to correlate weight with height, some people may simply combine it with Spearman, and the other ones may report Pearson. Then you can kind of decide to combine the two. They are not very far away from each other, so you can combine them. You could be conservative. And say, no, I want to combine them. But it's your decision to combine them. But statistically, it's possible to combine the two correlation values. Yeah, but that's what you need to know. Is that you need to transform the correlation values and proportional correlations. Usually skewed distributions, so to avoid this skewness, then you have to transform them. For proportion, we have seen logit transformation, and for correlation, we have seen z-code transformation. But this transformation, you will also use it for group designs. For example, if you are working with combining risk ratios and odds ratios, you will need it to transform the values into logit transformation. And there are also other transformation methods that you can apply for before combining odds ratios, risk ratios, and other skewed effects and measures. Yeah, that's for today. Next, I will I will talk about effect size measures for control groups. If you have like group 1, group 2, or maybe more than that, and we'll talk about that. And one of the most major is mean difference, continuous outcome. We'll talk about that in the coming sessions, and then once we get into that, we will be diving into combining the studies. And actually, I will also talk about how you extract, how you sometimes you may have values that you need, the study may not report the values that you need. So in that case, you may have to calculate from the reported values. There are ways to calculate, for example, if your study reports it doesn't have standard deviation, and that it has a mean and median or range or something, there are ways to calculate one value from the other. I will show you those techniques before actually diving into synthesizing and doing data analysis. I mean, once the most difficult part is getting the data and getting reading the data. Once you have the data, the next is just applying the software can do it for you. It's just passing the functions, the right arguments with the right solution. That's all for today. See you next time. Thank you.